Hello and welcome to today's webinar, Running DSP Algorithms on Arm Cortex-M Processors. I'm Jacob Beningo, and I will be your host and lecturer for today's session. Before we get started, I would like to go over a few housekeeping items. First, this webinar is being recorded and will be provided to you in a follow-up email. Next, in that email, I will also provide a link to a white paper that has been put together that provides additional information on this topic. And then finally, if at any time you have questions, please feel free to enter your questions into the Q&A text box, and I will answer your questions after the lecture portion of this webinar. As I mentioned, my name is Jacob Beningo, and I am an independent consultant. I've been running Beningo Embedded Group for 10 years now and have had the opportunity to work with clients in more than a dozen countries around the world to help them with their embedded system design challenges. I've assisted in areas ranging from product development, performing software audits and analysis, improving processes, decreasing debug times, and acting as a technical advisor. You can see on this slide a few ways that I interact with my clients and the embedded systems industry in general. I also develop a lot of free material on how to design systems that you can find on my website at beningo.com or in my monthly newsletter, Embedded Bytes. Now in today's session, we are going to be discussing how we can run DSP algorithms on a Cortex-M processor. Now, since all of us are coming from different backgrounds, I'm going to start with some fundamentals. I'm going to give you a little introduction as to why DSP is important. We're going to talk about DSP fundamentals. I'll talk about the ARM DSP ecosystem in general, some of the tools that are available and some of the companies that are doing really cool things in the DSP area. We'll talk about some of the common DSP algorithms that are used in embedded systems and how those apply to some of your applications. Then I'll talk about some of the ways that we can go about speeding up these DSP algorithms on an ARM Cortex-M processor. So we're going to talk about some of the optimization techniques and how we can use CMSys DSP library in our applications. And then finally, I'm going to close with a couple of best practices and then provide you with some information on how you can go further and learn more about how to run your DSP algorithms on the Cortex-M processor. So why are we talking about digital signal processing today? Well, digital signal processing is a really key and critical component within an embedded system. And especially today, as we start to look at all these connected IoT-based solutions, we're starting to see that there are sensors literally everywhere. So the IoT is really proliferating sensors. And of course, if we're connecting these sensors to digital systems, we need to make sure that those systems have clean data to work with. And we want to make sure we don't have artifacts or noise inside of those signals. So we can do that in a couple of different ways. We could first do it in hardware, which my last webinar, we actually talked about how you can decrease BOM costs by moving some of those hardware filters into software, which brings us to the second way of doing things, which is to do the signal processing in the actual microcontroller. Now, there's a lot of benefits to processing the signal data inside of our microcontroller. And we can do this using a special microcontroller that has digital signal processing extensions. And some of the benefits to doing this is that it provides us with additional flexibility to use the same hardware in a lot of different applications. It may allow us to easily adapt our system to work in a lot of different environments. And it also helps us to minimize product size and energy consumption. So for example, if I can move some of my hardware filters into my microcontroller and let it process them very quickly, I might be able to save on some of the leakage current that might occur in my actual system and decrease the size of the actual overall product. And these benefits are really important because of the applications that we're starting to see in the IoT space. So you can imagine easily within the IoT space, we have sensor nodes absolutely everywhere. If you start looking at things like maybe say a smart building, you might have these devices all over the place and on panels and rooms. You might have airflow sensors, temperature sensors, things that detect whether doors are opened or closed. There's all kinds of things that are being done with sensor technology. And some of the pieces of this is we might start thinking of applications that this is applied to in different spaces, but a lot of it can be thought of in a general sense. So we've got applications like IoT, we have traditional motor control that it really uses a lot of digital signal processing. And we also have things like machine learning, which are kind of cutting edge technologies that are starting to find their way from the cloud and moving to the edge that we have to be aware of as embedded systems developers. So from this standpoint, this is some of the reasons why we're starting to find an increased need for digital signal processing in our microcontrollers. And the need has always been there. I think the demand is growing because of the IoT. at ARM TechCon, I came across a really interesting example from a company named Chirp. And basically what Chirp was doing is they are kind of like a audio QR code. So basically what they're doing is they're using sound waves to allow you to transmit data. And basically what's happening is that data is being sent over near ultrasonic sound waves. And you can see here on this slide, there's an example of a card that they developed with Microsoft. This Microsoft Azure MX chip that includes the Chirp solution on board. And basically what it is doing is it's allowing you to use digital signal processing to convert data to sound, transmit it to another device somewhere else that then hears the sound and converts it back using digital signal processing back in the data, and then it uses that particular data. And it does so in such a way that makes the transmission of data secure. People can't hear it because it's near ultrasonic, so you don't even know that the sound waves are there. It's very low power, and it provides people with a very simple solution to be able to interact with perhaps an IoT device or set it up. So the example that I actually saw was that, we always have these Wi-Fi access points, right? And the way that we set these devices up, or, you set up a new Alexa or whatever the device is, it always broadcasts as its own Wi-Fi network to start. And then you have to go and join that Wi-Fi network, open up a specific web page, and then enter in your Wi-Fi configuration, and then it starts to act like a typical device on your network. But that's it's a pretty big step to go through and do that. It's time consuming. And what this actually does is it could easily allow you to go through and instead from an app over sound, send the device your SSID and your password without having to go through that whole, convert this to an access point, now join it, a very time consuming process. So it can really streamline a process. And I think this is very interesting and cool because it's actually using digital signal processing in a Cortex-M4 and M7 type of environment. And it's actually using the DSP extension. So this is kind of a real good example of some of the things that we're going to be talking about today that's already out there and is being used in industry. And if you happen to be interested in something like this, ARM actually put together a white paper called Data Over Sound. And you can find the link to that white paper right here. And that'll give you a little bit more information about this particular solution, but there's also some information on how that's done as well. Let's now dig in and do a quick review of what it is that we're actually trying to accomplish when we're doing digital signal processing on our embedded systems. So you might recall, and this may be you may already know this, or it might be that this is a review and you haven't seen this in a decade or two. But the idea here is that we typically have had some type of digital signal processor when we want to do DSP work with algorithms. And these digital signal processors in the past have typically been fairly expensive. They're very dedicated processors. They're very good at doing mathematical computations. And what you can actually do now in this system is you can actually swap out these expensive digital signal processors, and you can go with a standard microcontroller that has DSP extensions. And what the DSP extensions allow us to do is actually perform very complex mathematical functions very efficiently on a microcontroller. Now, a traditional DSP actually doesn't have a lot of the, it's very good at doing math, but it isn't very good with interacting with the outside world. Whereas our general purpose microcontroller is very good at interacting with the outside world, but if it doesn't have the DSP extensions, it's not that great at doing math very efficiently. So we kind of have in these DSP extensions the best of both worlds, where we have a resource-constrained, inexpensive microcontroller that's also capable of performing DSP calculations quickly and efficiently. And there's lots of techniques that you can use to do this that we'll talk about a little bit later in today's webinar. But what I want you to keep in mind here is that we're going to first have our microcontroller here in place of our digital signal processor. We're going to have our microcontroller interact with the external world, this analog world, using an analog to digital converter and also a digital to analog converter. And what we have here is you can actually consider these two pieces to be basically a codec. And you would imagine this to be something that is perhaps on an audio card. You might find if you go and you look at some of the different websites that have those shields that go on top of development boards, you'll find that some of them are really good DAC cards, some of them are really good ADC, some are designed specifically for an audio card, and they have both. You don't always need an external ADC or an external DAC. A lot of microcontrollers nowadays are actually very sophisticated. So for example, if you use something like a PSOC 6 from Cypress, they have really good ADC capabilities on the microcontrollers. And they have really good DAC control as well. So you might not even need an external audio codec hardware in order to perform any type of digital signal processing. If you do, a lot of times what you'll find, especially if you're working with audio applications, you'll find that you'll usually use the I2S interface to easily interact with those devices. So you'll use I2S and maybe I2C as a side channel to actually communicate and control the particular IC. But those are a couple examples of different ways that you can kind of build a system up if you're going to be doing some digital signal processing. And then, of course, on the ADC side, what we want to do is we're trying to sample an analog signal. So we have some signal that we're interested in. We want to be able to digitize that analog signal and get it in a digital form that we can actually manipulate in our code. And then perhaps if we wanted to then generate some external signal. So, for example, when we're thinking about the chirp solution, on one side, they're reading in the audio sound that's coming in. They want to digitize it. They want to get the data from it and decode it. But then on the other side, they're trying to actually produce the sound so that they can maybe send back a response. So in that case, we need to be able to convert our digital signal back into an analog equivalent so that we can transmit that out. So these are kind of the main pieces that we're going to be looking at today. Most of our focus is really going to be on the analog to digital conversion side. We're not going to look a ton on this side, but a lot of the techniques that we're going to be talking about here are easily applied to the other side as well. If you think back to when you took your digital signal processing class in college, if you ever did happen to have one, basically what we're doing here when we're trying to convert our analog signal into a digital signal, we're going to be having, this is a continuous signal in the analog domain, or in the time domain. So what you have here is a continuous signal, and what's going to happen is our microcontroller, our analog to digital converter, we're going to be periodically sampling that signal. And what we're going to end up with is so many samples over some period of time, and each one is going to be represented and spaced by a period of time. And what we're going to do is, from that analog digital sensor time, we're going to get an idea of how the signal is actually changing over time. And in order to sample that sensor inside the analog to digital converter, what we actually have here is some sampler. So we have our signal here, which is represented by some function x of t. We're going to have a sampler within our analog to digital converter, which is going to sample. We're going to have some quantizer within that allows us to provide an actual digital value. So, for example, a lot of times you might have an analog digital converter that gives you 0 to 1023 for values. Maybe you'll have 0 to 4094 or 4095. So you can imagine here that we have something that's going to quantize whatever the value is that's coming in, that's sampling, and give us a representation of what that actually is inside the real world representation of the signal. And the hope here is that, here's a signal that we're trying to sample, and digitally we have just set values spaced over a period of time that represents what that signal is doing. Now, of course, it's possible in between our samples, the signal could be going all over. So we have to be very careful how we go about selecting our sample rate and making sure that that we're not going to have any problems with the signal or that we misrepresent it when we're actually reading it in. Now, one of the big problems that developers can potentially come across, depending on their application, is that we have this problem called aliasing. And basically, aliasing can occur when the sampling rate of the signal is less than 2 times the highest frequency component in the signal. So basically what we do whenever we're trying to use our analog digital converter, we really should be saying, okay, what signal is it that I'm actually interested in? And then we should look at that analog signal, and we should put an anti-aliasing filter in line, or do it in our software as well. It can be done in multiple ways. And really what we're trying to do with these anti-alias filters is we're trying to restrict the signal bandwidth to the frequencies of interest. So instead of allowing my analog to digital converter to, accept all frequencies and whatever it is that it possibly can, perhaps I'm doing some audio application. I'm only interested in frequencies between maybe 1 hertz and let's say only 10 kilohertz. So there's no need for me to be accepting signals of, anything over 10 kilohertz. So at that point, I want to make sure that I have filters in place that will limit the bandwidth to just the frequency range that I'm actually interested in. And on top of this, within that frequency range, I want to make sure that when I'm sampling and setting up the rate at which I'm going to sample the sensor, I want to make sure that I follow Nyquist's theorem. And basically what Nyquist's theorem states is that in order to digitize a signal accurately, you must sample the signal at twice the highest frequency component in the signal. And that will make sure that we successfully are able to digitize the analog signal. And a great example of aliasing is if you've ever watched, a television show where you actually see a car that's driving down the road. If you watch the wheels, you'll notice that as the car is driving, the car looks like the wheels are turning in the right direction. But over time, all of a sudden, the wheels, they'll start changing direction, and sometimes they'll actually look like they're going backwards. And the reason for that is that the sample rate of the frames is not twice the maximum frequency of the actual spin of those wheels. So what happens is those wheels are actually being aliased in the frame, and you don't get an accurate representation of how those wheels are actually spinning in the real world. So that's a real simple example that you can check out whenever you're sitting there just watching TV. That's a real world example of how aliasing can affect how a signal looks when it's being digitized. Okay, so that's just a real quick background or review on some digital signal processing basics. I just want to make sure that we're all on the same page and that you have kind of those real basic fundamentals down. So let's now dive in and start talking a little bit about the capabilities and features of the Cortex-M that would include a digital signal processor extensions. Now, a couple of things that we want to keep in mind, or a couple of features that are really important to us. We want to make sure that as we're designing these algorithms, you want to take into keep in mind, are you using floating point or fixed point mathematics? Now, we can do digital signal processing on any microcontroller. You don't have to have DSP extensions. But what you'll find is that if you don't have DSP extensions, your code size is going to be a lot larger because you're going to be using libraries that are designed to kind of emulate floating point mathematics. So, for example, you'll end up with these fixed point libraries. A perfect example, there's a series of microcontrollers I've used in the past that were designed for motor control, and they didn't have DSP extensions. So we really had these huge libraries that you had to bring in, and all of the mathematics was actually done using a software library. And they're slower, they take up more code space, which means you can't really get your processor in low power modes. There's a lot more effort to really get these libraries to work the way you expect. Versus if you have the DSP extensions and a floating point unit, a hardware floating point unit, you can actually use the floating point math, and the calculations are extremely fast, and they're usually deterministic, which I'll show you some interesting data here just shortly to kind of help enforce that point. What's also interesting is that when you have DSP extensions, we have things like saturating addition and subtraction instructions. We have things like multiply and accumulate instructions, which are really important if we're going to be doing IIR or FIR filtering, which we are going to be talking about here in just a couple of minutes. We'll go into a little bit more detail on what those are, but they're two algorithms that are very commonly used in embedded systems for filtering applications. There's also a really cool instruction called SIMD, and what SIMD allows us to do is it's actually a single instruction, but it allows you to process multiple pieces of data simultaneously. So if you're working in audio or video applications, which typically use only 8 or 16-bit integers in the mathematics, you don't really need anything higher precision than that. What you find is that you can actually operate on multiple pieces of data simultaneously, which means the algorithms you're going to be running on your system can be executed twice as fast if you use the SIMD instruction. And I'll show you how we can actually use that here shortly. Now, ARM has put together some libraries that are very useful to a developer who wants to do digital signal processing. So we don't have to know necessarily all the low-level instructions and details of the actual microcontroller. Instead, what we can do is we can leverage the CMSys DSP library. And this has algorithms built in to do filtering, basic math, statistics, to do the transforms and matrix functions and all kinds of really cool things. Now, a lot of times what you'll find is that this library is actually included as part of your tool chain. So you may not have to go out and download it. For example, if you go and get Kyle and create a project, you'll automatically see that you have a CMSys tab there inside of your project. So a lot of times it'll be automatically brought in based on what you're trying to do. But if you're using something like GCC and some open source community type of IDE, you may need to actually go and download the CMSys libraries. And what you'll find is if you go to GitHub, github.com, go to ARM software, and then right now under CMSys 5, you can find the latest library to download it. It actually includes more than just the DSP library. It includes all of CMSys. But from there, you can get the CMSys DSP library and kind of dig through and see all the features and functionality that's there. There's actually over 60 different functions that are there to help us as developers more easily implement our digital signal processing algorithms. So you'll find that, for example, doing an FIR filter is as simple as calling creating the table of coefficients for our filter, and then just passing the data into a FIR function, and then at that point, it automatically does all the math behind the scenes for us. So really simplifies development. Beyond looking at libraries, we also have features and tools and other companies that are out there that are developing capabilities to really help us streamline this. So if you're going to be doing a DSP application, you don't necessarily have to start at the lowest level of development and work your way up like we traditionally do. You can actually start with high-level tools. So for example, a couple of tools that I've used in the past, whenever I'm trying to do filter design, for example, I've used this ASN filter designer, which is an example right here. So if I have an FIR or an IIR filter I want to design, I can literally come in here, and you can see this red line here. I can click on these points and I can drag it around to get the gain that I want of the filter, and also to get the pass bands that I'm interested in as well. Or I can go in on the right hand side here and select the filter type, what method of filtering I want to do, and this tool will actually generate the algorithm automatically for me, and I can take it, copy, and paste it into my code. And then if I need to make adjustments, I just come back to the filter designer instead of some Excel spreadsheet, and then have to keep redesigning everything. So it actually generates the coefficients and even the calls into the DSP library that are required to make the algorithm work. So that ends up being pretty cool. I'll show you an example of how you can actually set that up a little bit later as well. And then there's high-level tools like MathWorks' MATLAB, which we can use to design control systems and filtering and lots of different things. And then there's other companies that create software components for example, for intelligent sensors, this Hillcrest Labs, and voice and facial recognition, like recognition technologies, software libraries. There's a whole bunch of capabilities out there. So what I'm getting at is we don't have to redesign the wheel or design the wheel from scratch. There's already a lot of capabilities out there for us that we can leverage to help us speed up our development process. So you can learn a little bit more about those here. There's a link here for the developer.arm.com website under Technologies, DSP, Arm DSP Ecosystem Partners. There's a big list out there. I just kind of grabbed a couple of the ones that I thought were most interesting to show you a representative example. Let's start getting into some of the details of what types of algorithms we can use in our embedded systems. Now, there's really four very common types of DSP algorithms that I find in embedded systems. The first is a moving average. Most of us are very familiar with this. It's just we take a sample on our ADC sensor peripheral, and we average it some number of times, and we get some moving average of what the data is. We also have FIR filters, which tend to be very stable filters, where their impulse is equal to basically the filter coefficients. So I'm going to try to avoid going into super heavy math. I'm going to keep it very high level. As many of you know, if you get really deep in a DSP, I mean, you can get very deep in the mathematics. That's not the point of this webinar. We're going to try to keep things very high level. So just be aware. There's coefficients that are filtered. And I'll show you the equation here in a little bit and what exactly that is. But the FIR filter, basically your impulse is equal to the filter coefficients. We have infinite impulse response filters that are potentially unstable, but their impulse is computed recursively from the filter coefficients. So basically, the FIR filter doesn't use any of its output as part of its input to calculate what the filter is going to be doing, whereas the IIR filter actually does. So it uses the output as part of its input. So we get this recursive feedback in the algorithm. And then we have fast Fourier transforms. And these are normally very computationally efficient algorithms for calculating a discrete Fourier transform. And basically, beyond the definition, basically what we're doing here is we're trying to basically filter out noise from our signals. And for FFT, we're trying to convert a time domain signal into the frequency components of the signal. Is basically what we're doing there. So these are kind of the four main signal types of algorithms for DSP that I see used in embedded systems every day. So let's start talking about some of these. Now, a moving average, this is probably the one that you're most familiar with. A moving average just basically filters and smooths out the input signal. So what this is basically doing is that it's filtering out or blocking high frequency signal components. So if we get some data that's way off, high, basically we're trying to get rid of high frequency signals inside of our signal. And what this does is it basically acts as a low pass filter is really all it is. And you can see here in this picture representation, we have some moving average filter. We have X number of inputs, and it generates some Y output. if we were looking at something like a 5-point moving average filter, then the output is just equal to, the sum of 5 of my samples divided by 5, and that just gives me the moving average of the signal. Now we can, of course, represent this in a more generic form, which you can see here as just a summation as 1 over n, where n is the number of samples, and x is, of course, the function that represents the signal that we're interested in, and we're sampling it n number of times. So if I have 5 here, 5 gets sampled in here, we go from 0 to 4, 1 over 5, and basically when you expand that out, you just get this signal up here, or this equation up here. Now, as I mentioned, what's interesting about this is, this actually is a low-pass filter, but for most embedded systems, I really don't see teams that ever go through and think about what the actual filter response of a moving average filter is. We just normally say, well, I'm going to average 5, or I'm going to average 10, and we just kind of pick a number. So one of the things I do kind of want to point out here is that if you're using a moving average filter, it's useful to actually go through and figure out what the frequency response of that signal actually is by doing your average, and to determine if that actually makes sense for your application. The finite impulse response, FIR filter. Basically what an FIR filter is it's an endpoint moving average filter. So what you see here is the general form of an FIR filter is this equation right here. Now, if you, so this is our, if you look on the previous slide, this looks pretty familiar here. This is actually our moving average. So the moving average filter that we usually apply, or that we use in our applications, it's actually a FIR filter. So when I said that there's 4 different types of filters I see, it's really just 3 types. It's just most people don't refer to their average filter as being an FIR filter. And what you find here is that we can compare this with the conventional representation of an endpoint FIR filter, which this is the equation here. So what you see here is that this 1 over n here, this is actually represented by h, which is a function of I, and that's actually the coefficients of our filter. So 1 over n in this case for our moving average filter, it's just our impulse response of the FIR filter. So when you hear me, occasionally talking about the impulse of these filters, that's just what this coefficient is, and for a moving average, it's 1 over n. So just something to keep in mind. I think it's fairly interesting that our moving average filter is an FIR filter, but we never actually do the math to see what the response of those filters are in our designs. So keep that in mind, kind of interesting. Now, infinite impulse response filters, IIR filters, these filters use previous output samples as well as previous input samples in order to calculate their output. So the IIR filter is recursive. It's waiting on, it's using inputs from its output of the filter, which of course is the reason why it can potentially be unstable. If you have an output that is going out of control, suddenly that out of control signal, which is on the output, is being fed back into the input, which can allow it to just blow up out of control. Now, what's interesting here is that if you take a look at FIR filters and IIR filters, an IIR filter actually contains a component of an FIR filter. So you can see here in the equation that it's, we have, as part of the output, we have an FIR filter, and then we have a component here, which is actually the addition which makes it an IIR filter here. So we have, you can look at an IIR filter, here's the whole thing. The FIR filter version of it is, a smaller portion. And you can see here in the actual representative diagram as well, we got the FIR filter, and then we have the feedback here from the full filter when we're doing IIR. So kind of interesting. Like I said, I don't want to go into the math. I'd rather start to discuss what's the difference between FIR filters versus IIR filters and how that looks when we actually execute them on an Arm Cortex-M processor. So when we're actually executing these devices, it's interesting to look at 3 different areas. So the first is computational speed. How fast can these algorithms actually be ran on my processor? What's the phase or the delay in the signal when I'm actually implementing this algorithm? And then what's the stability of the algorithm when I run it on a processor? And not necessarily just on a processor, but in general, how stable is the algorithm? So if we look at these filters, what we find is that an FIR filter is usually computationally slow, and it's a high order filter. And I'll show you here in just a slide what I mean by that, but it requires a higher order filter in order to get the same response as an IIR filter. Because of the feedback, what we find is that the IIR filter is normally faster than an FIR filter, and you can usually do it in a lower order filter. So that ends up being, when you look at it just that way, an IIR filter has an advantage over an FIR filter from a computational standpoint. But as we start to look at some of the other details, FIR filters tend to be, they tend to be more stable. So what I mean by that is that you're not going to have the filter run out of control. IIR filters are sometimes stable. You can design them so they're really nice and stable. But again, depending on what your inputs are, they can run away from you if you're not careful. So you have to be careful with an IIR filter, whereas an FIR filter is always stable. Now, an FIR filter also has a constant phase response or delay of the signal over the course of the frequencies inside of its filter. Whereas with an IIR filter, you don't necessarily have that same phase response. It can actually vary based on the frequency. Now, this isn't necessarily a bad thing, but it's something that you just have to be aware of when you're designing, one, your algorithm, but two, when you're acting on that algorithm. When you receive your data, you just have to be aware of the difference in that phase delay. So a couple of important points to just be aware of when you're considering using these filters. Let's take a look and see what this actually means from a frequency response standpoint. So if we take a look here on this slide, what you see here, again, I'm looking at FIR filters versus IIR filters. And you can see here, if I create a filter, one in FIR, one in IIR, both 10th order magnitude, what you can see here is that there's a pretty big difference between an IIR filter and an FIR filter. The IIR filter here, actually, you can see here, it's pretty constant across here, and it drops off very sharply for the 10th order magnitude here, or order filter. And if you look at the FIR response, on the other hand, it rolls off very gently. So if I wanted this, very sharp response, what I would discover is that I actually need to have a much larger order FIR filter to get the exact same response as I can out of an IIR filter. So for example, if I wanted to get the same response, I would actually have to convert my FIR filter to a 40th order filter to get a very similar nice sharp response here. So when we're looking at that again, as I mentioned, IIR filters are faster computationally, which means if I'm going to go to a 40th order FIR filter, this is going to be very slow to calculate versus just going to IIR. So if I can get the signal to be stable, an IIR filter could be the way to go computationally for us in an embedded system. But again, you gotta just look at your application and see what makes the most sense. Now, a fast Fourier transform is going to allow us to do a couple of different things in our system. So the Fourier analysis describes basically the transformation of a signal representation from the time domain into the frequency domain. So let's say I have a time domain sine wave that looks like this. Now, if I were to do an FFT transform, then what I would actually find is that maybe in the frequency domain, this is the representative frequency for my sine wave. Now, if I go through and I take my analog to digital converter and I start sampling this signal at some rate, what I might find is that when I take this signal and I do a transform on it, I'm not just going to have the signal that I'm interested in. I'm going to have signals across the frequency domain. So what ends up happening here is that we're also collecting noise and things like that that are part of the background of this particular signal that we're interested in. So what ends up happening here then is that I have these different frequency components, as you can see inside of my signal. And what I want to do is I want to actually apply this concept of a brick wall low pass filter. And what I can do is actually notch out here what frequencies is it that I actually want to allow inside of here. So I can actually convert my signal, time domain representation, into a frequency domain using FFT. I put that through a filter, and then what ends up happening is that within my signal, or within my digitized signal, I now have this representation for my signal. Everything else on the outside gets stripped away. And then I can convert that. If I convert that and reconstruct it back into my time domain, I end up with the original represented signal with none of the noise and all that stuff stripped out. So using those types of transforms can be very useful. It's useful for figuring out what the frequency components of a signal are. There's lots of different things that we can do with fast Fourier transforms. Now, it's important to keep in mind that when we're doing an FFT, we want to keep in mind that an FFT is a computationally efficient algorithm for calculating a DFT. Now, a DFT is actually just a discrete Fourier transform. It transforms a periodic discrete representation of a signal in one domain into the periodic discrete representation in the other. And if we're going to perform this on a microcontroller, it's important to realize that the FFT representation actually has fewer multiplications and additions in the algorithm than if you were to run a straight up DFT algorithm. And it's also important to realize that the more samples we have in the sequence, the better advantage it's going to be in actually calculating our FFT as well. I hope that gives you a little bit of a better idea of some of the DSP algorithms that we might want to run on a processor. So while we're thinking about these different algorithms, let's start to talk about how we can actually make them run quickly and efficiently on an Arm Cortex-M processor with DSP extensions. The first technique I'd like to talk about to speed up DSP implementations is the SIMD instruction. Now, as I mentioned earlier, this is a single instruction multiple data instruction. And what this does is it allows us to operate on packed 8-bit and 16-bit data. As I mentioned earlier, this type of data is often used in audio and video processing applications, but it allows a single instruction to process up to 4 different pieces of information, or depending on, of course, the size of the data. Now, the way that this is represented here is that you can see here, we typically have a 32-bit data that we operate on in a single instruction cycle. But if we pack the data together into, for example, say 16-bit data, there's actually 2 pieces of data in this 32-bit register. And what can happen here is in this memory location, I can actually process using SIMD both of these pieces of data on the same instruction. Or if I have 8-bit data, I can work on all 4 pieces of data on the same instruction. Now, as I mentioned, this can really help with throughput and efficiency of calculating these algorithms. A simple example here on how we can actually do this, I can create a Q7 data type here, which this is basically just saying this is 8-bit representation of the data that I want to look at. I have a couple of pointers, source and destination pointers for the data. And normally what you're going to do is you're just going to create an int32 data type. In this case, I'm calling it X. And we're going to work on this normal 32-bit register. So I can say X is equal to, and then I can actually dereference the pointer to get the data. And I'm going to say, hey, I want to look at the source data, and I'm going to use this _SIMD32 data type here. And what I'm doing is I'm actually going to pull this packed data into my variable here. And then what this is doing is afterwards, I'm going to increment this instruction so that I'm already pointed at the next piece of data so that I can basically try to move through this piece of data I'm trying to process as quickly as possible. So the SIMD32 instruction is pretty simple to use. This is just an example of how I take my packed data, get it into an int32, and then I can also do the same thing here when I'm actually trying to put the data back. I can say, here's the destination of where it's going, dereference that location using, again, the SIMD32, and then the data that it is I want to pack into that instruction. So it ends up being a very efficient way to be able to access, as I mentioned, audio and video processing data. There's a lot of other applications where you can speed things up as long as you're not, as long as you don't need that 32-bit precision. Another couple of things that you can do to help speed up your DSP implementations is to use the floating point unit that's on many of the Cortex-M4 and M7 processors. So, for example, just a couple of weeks ago, Jack Gansel published some data in the Embedded Muse in issue 369 that actually showed a real simple experiment that he did on a Cortex-M4F processor using the FPU. And basically what he did was he had set up his system to test addition, subtraction, multiplication, and division on 32-bit operations with and without a floating point unit. And what he did was he did the mathematics and he varied the number of parameters that he was passing into the mathematical functions. And what you can see here is if, from his data, if you take a look at the execution speeds of addition, subtraction, multiplication, division, and also the relative code size. So what he did was he built up his application. Then he said, okay, this is the general code size of the application. If I want to do, addition using no floating point unit, then this is, here was the result. Subtraction, required 12 more bytes, division, 20 less bytes kind of thing. And what he did was when he executed this and took measurements, he found that addition took 181 to 321 nanoseconds. Kind of non-deterministic, depending on how many parameters you passed into the actual function for it to calculate. But you can see a pretty wide range of values that perform these calculations, 181 nanoseconds all the way up to 533 for division. So we're talking, quite a fairly significant amount of time here without the floating point unit. But once he enabled the floating point unit, addition, subtraction, multiplication, division, no matter how many parameters he had passed in his experiment, addition, subtraction, multiplication took just 17 nanoseconds to execute. It was very deterministic, and the division time was 83 nanoseconds. So you can see here that if you're going to be doing digital signal processing, you really want to pick one of those processors that includes the floating point unit. It dramatically increases the efficiency of the processor, the rate at which you can actually crunch through your calculations. And you can see here it also decreased the relative code size here. So where we had no FPU, we're obviously bringing in some type of library to perform the calculations. That requires more clock cycles in order to get the job done. When you're using the built-in FPU, it's more deterministic. One, because the FPU has a lot of registers. It has like 30 registers to be able to actually perform the calculations. It's separately hardware-based, so we're not bringing in also a separate library, so it also decreases our code size since the calculations are being done in hardware. So it's really cool. I'm glad that he had put together this data. It was perfectly timed for this webinar and saved me from having to go through and perform these calculations myself to share with you guys that, hey, look, that's a pretty big difference. An order of magnitude of almost like 10. In the least case, in many cases, a lot more than that. Okay, so what are some other strategies that we can actually follow in order to try to optimize our algorithms? Now, there's quite a few of these. I'm going to tell you a little bit more about this later, some additional resources you can use, but one of the really good resources if you really want to understand at a low level what the processor is doing, especially for digital signal processing, I highly recommend that you read The Definitive Guide to Arm Cortex-M3 and Cortex-M4 Processors by Joseph Yu. Now, this particular book, chapters 21 and 22, cover everything about DSP. Chapter 21 actually covers the low-level hardware-related things for developers, and chapter 22 covers the CMSIS DSP library. But I'm telling you this now because a couple of these strategies I actually borrowed from chapter 21 out of this book. So I just wanted to let you know that some of them did actually come from Joseph there and not from myself, just to give some attribution there. So, but in any event, these are a couple of really good strategies that you can use in order to help optimize your algorithms. So first, use group and store instructions to save a cycle per operation. Basically what happens is if you have isolated load and store instructions, it's going to require 2 clock cycles for each one to load and store. But if you group all the load and store instructions together, what will happen is that it'll take two instruction cycles on the first one and then 1 instruction on every one that follows after that. So that can be a real good way to dramatically increase the performance of the system. So basically what ends up happening is instead of it being 2n, where n is the number of load and store instructions, the equation becomes n plus 1. So almost a 50% savings there if you group those together. And some compilers will be good at doing that on its own, but depending on what optimization level you have set on the processor. But it's also good as a developer to try to keep that in mind as you're running your software. You do want to experiment with the compiler optimization settings. There's obviously different settings for the compiler, 00, 01, 02, 03. Take a look at those. From looking through some of the Arm Cortex-M materials, it sounds like they found that setting it just at 03 and expecting the compiler to know isn't always the case. Sometimes 03 actually doesn't group load and store and other instructions together properly. So you actually have to experiment with this in order to really achieve the most benefit. You can also use things like loop unrolling to decrease overhead. So this is where if you know that you have to loop through this 4 times, instead of going through a for loop for the 4 iterations, you tell the compiler to unroll the for loop for up to 4 loops, and you do that intrinsically at the actual function using compiler intrinsics, which aren't portable, but it'll make the code more efficient to execute. So what happens is it unrolls that loop, and then at that point, the code size will go up a little bit, but the speed of the execution of that code will be far faster. So keep that in mind as an optimization strategy. When you have these DSP algorithms, what you'll find is that a lot of times they'll have some inner loop. So it'll be multiple for loops kind of nested together. And where you really want to focus your optimization is on the inner loop, the loop that's in the middle of all those. Because what happens is that inner loop is what is actually doing most of the work, and it's being called by all those other loops, multiple times. So the area to actually optimize is inside the inner loop. You also want to make sure that you select the right variable precision. So for example, if I'm doing something that only requires 8-bit precision, I shouldn't be using 16-bit or 32-bit precision. Instead, I should make sure that I select 8-bit, which is the most I need, And then I can use things like SIMD to operate on multiple pieces of data simultaneously, which will then allow me to be a lot more efficient in my algorithm. We also want to minimize the order of our filters. So for example, if I can get away with using an IIR 10th order of magnitude filter, that may be better off from a calculation standpoint. That's going to be far better than doing like an FIR 40 filter. So or maybe even a 20. So be very careful how you pick your filter. Don't over design it. Design it in such a way that it meets your needs and applications. But I think as designers, we have a habit of over designing at times. So be careful when you are designing those. And then use lookup tables. Lookup tables are a great way to very efficiently not have to calculate things. So just have a lookup table that you can easily index into to grab a value rather than actually have to calculate it. And then at that point, you're just using the instructions to go out and fetch a piece of data rather than dozens of instructions to actually calculate what that value is. So it can really help speed things up quite a bit. Now, I didn't want to leave you without providing you with some type of example that you can follow on how you can implement some of these things. So while I'm not going to be showing you a live example today, one of the things I do want to kind of point you to is one of the ways that you could implement this, and I'm going to walk through a couple of steps here, is I had a PSOC 6 development board from Cypress. And this is actually a secure microcontroller that has a lot of capabilities in it. But it includes a Cortex-M4 processor that can be used for digital signal processing. And it's got the DSP extensions built into it, in addition to a secondary core, which is a Cortex-M0 Plus, that's actually used as a secure processor for secure IoT applications. Since we're talking about DSP, though, I'm going to focus a little bit more on the Cortex-M4 side of things here today. Okay, so let's dive in and take a look at how we can design this filter. Now, one of the tools I talked about in my last webinar was ASN Designer, and I really like this tool for designing filters. I haven't come across anything else out there that is quite as versatile and has all of the capabilities that this tool has. So one of the things that you can do here is you can go in this ASN Filter Designer. As I mentioned earlier, we can drag these red spots around to design what the bandpass should actually be for this particular filter. And then I can actually go in and tell it to generate the DSP code for me, the CMSys DSP compatible code. And what you can see here is it generated the code. And then what I did is I went into the PSOC 6 development environment, and I copied and I pasted the algorithm code into my development environment. So what you can actually see here is starting here at this include up here, I pasted this in. We can see there's some sample data that's automatically generated. The block size for this filter is in there, along with output and input values. It actually creates the arrays for me. It creates some pointers to these that we're going to use later. It goes through and it says how many sections there are in my filter. So there's 3 sections. You can see here, section 1, section 2, and then section 3 right here. We can see here that my coefficients are calculated automatically by the tool. And then those are going to be used in the actual algorithm. And then what I do is I copied and pasted in the main piece of the algorithm, which is right here, into the designer. And then I can deploy that onto my PSOC 6 development board. Now, to dive in a little bit deeper here, what you can see here is in this main function, I'm making calls to CMSys DSP. So I'm using those libraries, and I'm deploying them quite easily here. So you can see here, they're calling the initialization for our calculation here, Arm biquad cascade, a DF2T init, and basically, again, this is all generated by the tool. It actually knew these are the Arm DSP functions that I need in order to properly calculate the IIR filter. So it initializes some biquads here, and then we call this Arm biquad cascade. And this is this biquad cascade. This is just a technique that we're using to implement the IIR filter. I know we didn't talk a lot of detail about that, but you can investigate that a little bit further on your own. The actual calculation is done here. You can see here we have a loop, and then we just pass into this DSP function the input value, so what it was, perhaps what we read off the ADC, the block size, the output values, and so on and so forth. And then at that point, we just let this thing go through the loop, and it will go through and calculate the values for us and place the generated output into our output buffer. So you can see here, this ends up being pretty easy to design our filter, move it into our environment, and then at that point, we just have to deploy it. And in most IDEs, what you're going to find is that you don't have to do a whole lot to get this to work. But as I mentioned, so for example, if you use Kyle, a lot of times this is automatically pulled in. If you're using something that's GCC based, you might have to do a little bit of extra work. Maybe CMSys doesn't show up, or you have to dig into the compiler libraries to figure out exactly where CMSys is located. I found that sometimes a real easy way to do this is just to follow a couple simple steps. First, you can download the CMSys library from GitHub, or you find your local copy. Once you've done that, you do need to add in a project include reference to the library of interest. So, for example, if you look at the directory structure for the CMSys library, it goes CMSys DSP and then the include directory. And at the CMSys level, there's things like DSP, RTOS, neural networks, and all kinds of other cool things that are in there. But you want to make sure that you include the DSP library. Within the Cypress PSOC 6 environment, I also wanted to go into my properties for my project. And when I go under the GNU ARM Cross-C compiler under preprocessors, I had to add in ARM_math_CM4. This just tells the tool chain that I'm working on a Cortex-M4 processor, and I'm using the ARM math libraries. At that point, I would go into my project and I would add the source files for each of the individual functions I'm using, or I would just grab the precompiled library and add that as a reference. It just depends on whether you want to be able to move through the source easily or not. And at that point, you can compile your code, deploy it onto the PSOC 6, and you could run the code and see how the test filter works, but then you could also attach the ADC inside of there and generate and actually push like a sine wave or something through it and see how the filter actually behaves. So it ends up being a pretty cool way, I think, to go from beginning to end to see the entire gambit of how things work. As I mentioned, though, I'm really leaving that to you guys to do today to actually try it on your own. Now, we've talked about a lot of things in just the course of this last hour. I want to leave you with a couple of best practices for running DSP algorithms on ARM Cortex-M processors. And I obviously can't cover all of these again in detail since we're running a little bit short on time, but I do want to leave you, I think, with some of the important ones. First, I want to make sure that you leverage existing tools that can automatically generate code for you whenever possible. Don't reinvent the wheel. A lot of times, I think as developers, we think, oh yeah, I can do that better, or I don't want to spend $500 on that tool, I can do it. It ends up being a lot easier to just go and get things that already exist. Trust me. I've gone through all of that myself and with, dozens of my clients. And in every situation, I've always found it just easier to go out and get something that someone else has already done and integrate it into your software. Another best practice I think I'd like to have you think about, read Digital Signal Processing using the ARM Cortex-M4 by Donald S. Ray. A really good book that talks about digital signal processing. This book does get into the low-level details of digital signal processing from a mathematical standpoint. Really good book, but it also has code that is associated with it, so you can deploy it on some development boards as well. I think you have to review Chapter 21 and 22 in the Definitive Guide to ARM Cortex-M4 and Cortex-M4 Processors by Joseph Yu. Really great book overall. There's lots of other really good information in there, but at least the digital signal processing pieces are in chapters 21 and 22. A really good read. Definitely take a look at it. Also, make sure as you develop your algorithms, monitor your CPU utilization and execution times. A lot of times you'll design your algorithm kind of high level, get it implemented, just see how it behaves, and then you can go through an optimization cycle. I'll usually do a rough cut of an algorithm before I go in and actually optimize it. I've found that that's quicker and efficient, at least for me to do. And it helps me, make sure that what I'm trying to do is possible first before I spend a lot of time trying to optimize something and then discover that, maybe I'm not going down the right path or something. So, make sure that you, keep those kinds of things in mind. I also recommend purchasing a development board to experiment with implementing FIR, IIR, and FFT algorithms as well. And also review white papers that are in your area of interest for digital signal processing. Now, a couple of resources for you guys to walk away with. Of course, feel free to visit Beningo.com, my website. I have a blog up there that covers some DSP topics, but I cover a lot of just in general microcontroller-based embedded systems development topics. So it can range from how you write a C driver or how you document your code all the way to artificial intelligence, digital signal processing, and security. Very wide range of things that I cover. A lot of that is actually covered also in my newsletter. So if you sign up for my newsletter, you'll get the pushes for my blog and get to find out other free resources and things that I'm doing that might help you as well. ARM has a DSP online course that you can find here at this link, along with more information on the DSP for Cortex-M processors at their developer.arm.com website. you can go ahead and follow that link. And I will include these links in the follow-up email as well. But if you want, snap a quick picture of it or something in case you don't want to wait until I get that out to you. There's also a really cool white paper on keyword spotting, which is a little bit more focused towards the artificial intelligence side of things, but I think it shows really well why digital signal processing is also important. So I recommend that you take a look at that. And then if you missed the last webinar I did on how to choose between analog hardware and DSP software, you may want to go back to that webinar. You can find the link right here. And in this webinar, I kind of go back and I talk a little bit more about the benefits of digital signal processing, the differences between a microcontroller-based solution with DSP extensions versus, a full-on out digital signal processor, and kind of cover a little bit more fundamentals there. So if that's something you're interested in, I highly recommend you check that out as well. These are an example of the 2 books that I recommend that you take a look at if digital signal processing is something that you're really interested in. Again, this covers digital signal processing from a theory standpoint and how you implement it on a microcontroller. This book, The Definitive Guide, really focuses in on how what features are in the Arm Cortex-M processor itself, and then strategies to efficiently run DSP algorithms. So I think paired together, really good set of resources for you. With that in mind, I just also want to tell you about a couple upcoming events. Next month on April 17th, I will be doing a webinar on securing embedded systems using threat-based analysis methodologies. So if that's something that you're interested in, I highly recommend you to follow this bit.ly link, BE-threat analysis, and sign up for that webinar. There are also other events that are going on. You can check out ARM's event page also at arm.com/company/events. You can also visit beningo.com. I usually post my events on the main page, but there's also within the menu structure there a link to other events that I currently have going on as well. At this time, I'll start answering the questions that have been put in throughout the course of the webinar. If you have to go, I greatly appreciate your time and attention and look forward to talking with you again soon. So let's dive in and answer some of these questions. Thanks again for your time and attention. I greatly appreciate it. I look forward to talking with you again soon.